Alright, so this is going to be a video where I go through Advent of Code 2015 Day 17, which has a really nice recursive solution that might help to explain a bit how recursion works. So, as a recap of what Advent of Code 2015 Day 17 is like, it's basically these elves have a crap ton of eggnog and they want to like perfectly put it into some set of containers that they have, right? And so in this example, they have 25 liters of eggnog and they want to put it into containers with these capacities, right? And they don't want to put any like partial thing. They don't want to put like 3 in the container that can hold 10. And our goal is to basically find how many different ways can they put all of this eggnog into these containers, right? So in this example case where you have 20, 15, 10, 5, and 5, and you need to store 25 in there, there's going to be 1, 2, 3, 4 different ways to do it. So we're going to have a function signature that's going to take all the containers that we have and the amount of eggnog that we're trying to store in these containers, and we return the number of different ways that these containers can hold that, right? So in this case, if you put this list into this argument and this into here, it should give you 4. Because again, 1, 2, 3, 4. And so because we're going to do a recursive solution, I have kind of set up here a two-step way of doing recursion. So our first step is basically just like, what are the ways in which it is, like, not necessarily like obvious, but you can just like say like either by definition or just like because it's such a simple situation what the answer is, and you just say what it is. So a couple of examples. So for factorial, it's like 1 factorial is just 1. Like it's like, I suppose in this case it's a bit obvious, and so what we would do in implementing factorial is that we start by saying, like, hey, if we have 1, just return that. Like, don't think too hard about that. Just like, if we get this input, just spit out that output. Fibonacci is another good example where, because of the definition of the Fibonacci sequence, the 0th Fibonacci term is 0, and the first Fibonacci term is 1, and that's just defined as Fibonacci. So we just say, like, we just check if we've gotten that as an input, and then output that, because that's part of the definition, right? And so the first step for this problem doing it recursively is obviously going to be like, what are the trivial solutions for this problem? And of course, remember, this is going to be the function signature. So there are 2 sorts of, kind of like with the Fibonacci, there are these 2 different ways in which the situation is trivial. And this one has 2 that you need to implement, and 1 that is a little optimization that you can do. But I'll talk about that at the end. I would suggest you pause here if you want to think about this a bit. And of course, it will have to do with like this signature having some very simple input, like with these situations. Anyways, if you want to pause now. If you've unpaused, here is the two situations. So the first, like, very simple or trivial case is that, like, we don't have any containers, but we still have some eggnog that we need to store somewhere, right? So in this case, we just say, like, there's no valid way at all to store this eggnog because there's no containers to put it in there. And the second trivial case is that we don't have any eggnog left to store. So that basically means, like, just if we don't use any of the containers to store 0 eggnog, then that is one way of doing it, right? So at the top of our function, we're going to basically check. This can also be less than or equal if you want to, like, protect against container count being negative. Of course, this is just like, I would normally use some other stuff to do this, but this is a bit simpler to have a range. We need a range if we want this to be fast. That's a bit of a side thing. But basically, these two lines are doing these checks. It's checking that we don't have, like, that if we don't have any containers, but we do have some eggnog we need to store, then, like, we can't solve this. And if we have no eggnog that we need to store, then that we do have a valid solution. And so the second part, and this is going to be a bit harder than that, is that we need to take some sort of non-trivial input and try and find something that is a bit closer to being one of these trivial cases, right? And somehow take the output of that and get something that's a bit, that we can somehow use that output to get our solution, right? So with the Fibonacci, or not Fibonacci, the factorial example, is like, if we have 5 factorial, we can get a bit closer to answering that we can get close to that question by basically asking, like, what is 4 factorial, right? So we, like, basically kind of separate off this 5 and figure out what is 4 factorial. And then whatever we get out of that, we just do 5 times that, right? So this would be 5 times 4 factorial. And to implement that, it's going to basically be like you call itself, but with, like, the 1 smaller, and do that multiplication so that you get the factorial. The Fibonacci example is pretty similar. Like, we might not know what Fibonacci of 8 is, the 8th Fibonacci number, but, like, we can use the 7th and 6th Fibonacci number to figure out that, like, to figure out what the 8th one is. And so, you know, it's just adding those two together, and that tells us what the 8th one is, right? And so just implemented here, it's going to do that, right? It is worth noting that this is exponential time unless you memorize it in part 1. But that is an advanced thing that I don't think we're expected to do in our class. But, this is exponential. Or the output is not exponential, but the time it will take to compute this is exponential. Anyway, so, of course, the question is, like, how many, or, like, not how many, but what ways in which you can take some input, for example, this 20, 15, 10, 5, 5, and 25 situation, right? How do we get this to be more similar to one of these cases where we have no containers or we have 0, like eggnog? And of course, here's the hint. There's a couple of different ways to do that, and you need to use both of them. So if you want to pause to think about it, do that now. And if you've unpaused, here is the way, I guess. So there's two ways that we can get closer to the trivial case. One of them, or both of them, involve like making a decision on this first container, right? So there are all of the ways in which you use the container, and there are all of the ways in which you don't use the container. And so, like, if we imagine a situation where we take this container that can hold 20 liters of eggnog, then, like, and we imagine we put 20 liters in there, we are now left with a scenario where we have 15, 10, 5, and 5 containers, and we need to put 5 among them because we took 20 out of here and we used up this container, right? So now we're left with, like, how many ways can we distribute 5 liters into these containers, right? And we can also imagine another scenario in which we never use this container with 20. We just straight ignore it. We don't bother using it. And so in that case, like, we just, like, take off that ignore it and don't bother subtracting out the eggnog because we never put any of it in there, right? And so if we figure out, like, how many ways can you do this where you use it, and how many ways can you do it if you don't use that one, adding those together should just give, like, the total number of ways we can do this with the option of using this container, right? And so that's where the sum comes in, and this is basically right here, is basically just a way of saying, like getting the rest of this as an array, right? Reference to this first one, so this becomes 0, 1, 2, 3. And of course, gotta subtract the container count by 1 so that, we go from 5 different containers to 4. So you gotta subtract that. And this is basically saying, like, subtract off the first container, the zeros container, I guess. Because in this scenario, we put the eggnog in there, and in this scenario, we don't. So we don't subtract it here, right? And so this is basically, like, the complete solution, but I'm going to first mention what that third trivial case was, and that was if we have negative eggnog. Like, that means, like, we don't have a solution. I mean, theoretically, if you had containers that like you could fill with anti-eggnog, and so you could have negative containers or negative valued containers, then like you wouldn't be able to do this, but we won't be given a negative sized container. So when we go into the negatives for the amount of eggnog, then we can just go like, well, we're not going to get a solution out of this, so that becomes 0, right? There are no ways to distribute negative eggnog among however many containers. So you can skip that. Anyway, so the final code I have right here, and it's in this other tab. And basically it's just like, it's the scenario from this, right? Where we have 20, 15, 10, 5, and 5, and we're trying to distribute 25 in there, right? So this is basically like putting it, saying like our containers, like go over them, over these containers, and what was it? And like figure out how many ways to store 25 in them. And it does in fact return 4, as in the beginning, 1, 2, 3, and 4. And so this is the solution, I suppose, to Advent of Code Day 17. And another tiny thing, like how I mentioned that the Fibonacci problem, or like doing the Fibonacci this way, means that you get exponential time, because when you call this 8, it becomes 7 and 6, and so this one is going to call 2 more, and this one is going to call 2 more, and each one of those is going to each call 2 more Fibonacci functions, right? Like, it just exponentially blows up, so you don't want to put anything more than about 8. This is kind of like, if you want to get like the 100th Fibonacci number, it will basically not complete in your lifetime. So you would want to do a different implementation if you wanted something that's actually fast. This scenario is, or this solution has the same problem. Of course, this is harder to simplify into something that isn't recursive. But like, this store function is going to call 2 of its own store functions, and each of those are going to call 2 more. So this does exponentially blow up the amount of time, and like, if you do this Advent of Code problem, and you might notice that like the input that it gives you is noticeably smaller than a lot of the other inputs, because like the solution kind of requires that you traverse something that exponentially grows like this. So it only gives you something that's like, 10 or 15 elements in the container. So worth noting the big O of N problem with this, but anyways, that should be it. This is effectively the solution. So anyways, hope that helped clear things up a bit. Bye.